In today's video, we will be discussing about Chemistry Paper 2 AS Level Structure Question 2023, October-November, Variant is 22 and the subject code is 9701. So the total mark for this paper is 60 and between 49 to 47 there is A star, 39 or its above would be A, 30 or its above would be B, 25 or its above would be C, 19 D and 13 E. Number 1. The elements silicon, phosphorus and sulfur are in period 3 of the periodic table. Discuss the variation in atomic radius from silicon to sulfur. So these are all pure 3 elements, and from silicon to sulfur, as number of protons increases, therefore nuclear attraction increases and so atomic radius decreases. The melting point for silicon is 1410. The melting point for sulfur is 113. Explain the difference. For silicon is a giant covalent structure with strong covalent bond, while sulfur is a simple molecular structure with weak intermolecular forces of attraction, and so more energy is needed to break the covalent bond in silicon compared to intermolecular forces in sulfur. Therefore, silicon has the highest melting point compared to sulfur. Then here we have given that we have to state the number of electrons. So for silicon there are 14 electrons, phosphorus 15 and sulfur 16 electrons. So after arranging the electrons in the orbitals, silicon contains 3p2 orbitals in the last orbital. Phosphorus, as it contains one more electron, so it contains 3p3, and sulfur contains 3p4 electrons. So the total number of electrons in S subshell for silicon is 1s2, 2s2 and 3s2, in total 6 electrons. For phosphorus and sulfur, these two also contain 6 electrons in s orbital. Then for p orbital, as phosphorus and sulfur contains one more electron than silicon, thus it also contains one more p orbital. So silicon contains 2p6 and 3p2, that means 8 electrons. So phosphorus contains 9 electrons and sulfur contains 10 electrons. So 8, 9 and 10. Consider an equation to represent the first ionization energy for silicon. Whenever we have to write the first ionization energy, we have to state the elements in gaseous state, and for silicon in gaseous state is converted to silicon plus ion and one electron is removed. Three possible values for the first ionization energy of P are given. Circle the correct value. So for P, that means phosphorus, we can say that for phosphorus we are given this ionization energy values. So for silicon the ionization energy is 786, for sulfur this is 1000. So phosphorus would obviously have the highest ionization energy compared to silicon, but it has more ionization energy compared to sulfur because sulfur contains spin pair electrons that causes repulsion. For sulfur in 3p orbital, we can see that as it contains 4 electrons, so there is a spin pair electrons that causes repulsion. Thus the first ionization energy for sulfur is less compared to phosphorus. So phosphorus has the highest first ionization energy. So it has a value that is greater than sulfur and obviously greater than silicon, that is 1060. So phosphorus has the greatest nuclear charge, then silicon, so greater nuclear attraction for outer electrons, while sulfur contains spin pair electrons that causes repulsion, so less nuclear attraction than P or phosphorus. Thus phosphorus has highest ionization energy compared to silicon and sulfur. Silicon chloride and phosphorus chloride reacts with water to form misty fumes. This misty fumes is basically hydrogen chloride, because when silicon chloride reacts with water, it forms silicon hydroxide and HCl. Also phosphorus chloride reacts with water to form silicon oxide and HCl. Also phosphorus chloride reacts with water to form phosphorus oxide and HCl. So HCl is formed. Predict the shape of the HCl2 molecule. So as sulfur contains 6 electrons, so it shares one of its electron with each of the carbon atom, thus it remains 4 electrons. Thus, for lone pair of electrons that causes repulsion or causes the bond angle to decrease, and instead of being a planar shape, it becomes nonlinear V shape with a bond angle of approximately 107 degree. Question number 2. Nitrogen oxide and nitrogen dioxide reacts at 25 degrees centigrade to give nitrogen 2O3. In 2O3, the reaction is reversible and reaches equilibrium. At equilibrium, the rate of forward reaction is equal to the rate of backward reaction, and the concentration of reactants and products reach a constant value. Figure 2.1 shows how the rate of the forward reaction changes with time. Initially, the rate of the reverse reaction is 0. So, initially the rate of reverse reaction is 0. On figure 2.1, sketch the rate for the reverse reaction changes with time. So, as the reverse reaction is initially 0, so it starts from 0. And at equilibrium, the rate of forward reaction is equal to the rate of backward reaction. Thus, the rate would be equal, and it increases from 0 until it reaches equal rate. State how the position of equilibrium changes if at all the reaction takes place at 100 degrees centigrade. So, initially the reaction is taking place at 25 degrees centigrade. Now it takes place at 100 degrees centigrade. So, as the forward reaction is exothermic, so increasing the temperature would shift the equilibrium towards the left. So, position of equilibrium moves to left since the forward reaction is exothermic. 2.1 shows the comparison of equilibrium mixture nitrogen monoxide, nitrogen dioxide and N2O3 at 101 kilopascal pressure. So here we have given the number of moles in equilibrium. Now we need to find the Kp or equilibrium constant pressure. So to find Kp, we need to first find the mole fraction, then partial pressure, then Kp. So to find the mole fraction, we know that the moles of each substance in equilibrium. So we divide the number of moles by that total number of moles, that is the sum of the total moles. Then we divide its number of moles by the total number of moles to find the mole fraction. After finding the mole fraction, we find the total pressure, that is multiplying the mole fraction into the total pressure to find the partial pressure. Then as we know that the partial pressure of each substance, and for Kp, the partial pressure of products divided by partial pressure of reactants. So it would be partial pressure of N2O3 divided by partial pressure of NO into partial pressure of NO2. So this would be partial pressure of N2O3, that is this value, divided by these two values, and these two values multiply with each other. So as the values are same, so we take square. So the final answer for Kp would be 0.0169, correct to its nearest value, and the unit would be, since for N2O3 the pressure would be, partial pressure would be kilopascal, and for the bottom, as there are two reactants, so it will be Kp square. So Kp cancels each other out, and at the bottom extra Kp remains, that is inverse as it is in bottom. So Kp inverse would be the unit. Identify one natural process and one man-made process that causes the formation of atmospheric nitrogen monoxide and nitrogen dioxide. So nitrogen monoxide and nitrogen dioxide naturally forms from lightning, since it requires high activation energy, because nitrogen triple bond is difficult to break. Also by man-made, that is internal combustion in engines, as internal combustion engines provide high activation energy to provide the nitrogen triple bond, to break the nitrogen triple bond and to form nitrogen monoxide and nitrogen dioxide. So it would be naturally lightning and man-made internal combustion engines. Nitrogen dioxide is a brown gas that is used to form nitric acid. So nitrogen dioxide is a free radical. Nitrogen dioxide is a free radical. What is meaning of free radical? Species with one or more unpaired electrons. So for nitrogen dioxide, we can see that as nitrogen contains 5 electrons, so it shares 2 of its electrons with one oxygen and 2 electrons with rest of the oxygen or with other oxygen, and 1 electron is remaining electron. So 1 electron remains. Thus this is called free radical. since it contains one or more unpaired electron. As it contains unpaired electron, that is, it contains one unpaired electron, thus it is called free radical. Then nitrogen dioxide is used in the oxidation of sulfur dioxide. So we have to write the equation for the role of nitrogen dioxide in this reaction. So nitrogen dioxide reacts with sulfur dioxide to form sulfur trioxide and nitrogen monoxide. Nitrogen monoxide is reactive, thus it then reacts with oxygen to form nitrogen dioxide. We can see that initially it remains nitrogen dioxide and finally it is nitrogen dioxide. So there is no change in nitrogen dioxide, thus it acts as a catalyst which increases the rate of reaction, or this causes the reaction and converts sulfur dioxide to sulfur trioxide. So it acts as a catalyst because there is no change in its form. Then state one environmental consequence of the oxidation of atmospheric sulfur dioxide. Sulfur dioxide is a greenhouse gas, or sulfur dioxide can be used, or it causes acid rain. Sulfur dioxide and nitrogen monoxide and nitrogen dioxide can cause the formation of acid rain, thus it is harmful for the environment. A student titrates nitric acid with a base to form a solution containing aqueous magnesium nitrate. Identify a base the student can use. So nitric acid reacts with magnesium hydroxide to form magnesium nitrate, and obviously magnesium hydroxide should be aqueous. Actually, as it is magnesium hydroxide, that means it is obviously in aqueous state. If it is magnesium oxide, then it should be in solid state, but since it is hydroxide, thus it is in aqueous state, since magnesium hydroxide is soluble in water. The student evaporates the water to obtain magnesium nitrate solid. When the solid is heated, it decomposes. Write an equation for the decomposition of magnesium nitrate. So magnesium nitrate decomposes to magnesium oxide, nitrogen dioxide and oxygen. As there is nitrate, we get nitrogen dioxide, and magnesium nitrate is converted to magnesium oxide, which is solid, and oxygen, or half moles of oxygen, to balance it. And as it is 1 mark question, so we don't need to write the state symbols. State how the thermal stability of group 2 nitrates changes down the group. So down the group, we know that the thermal stability for both nitrates, carbonates, sulfates, whatever it is, the thermal stability always increases down the group. Then in question number 3, phosphoric 5 acid, or H3PO4, is used in both inorganic and organic reactions. H3PO4 is man-made in two-step process from phosphorus. Phosphorus reacts with excess oxygen to form white solid. So phosphorus reacts with oxygen to form white solid. So we have to write the equation for this reaction. That is, in step 1, phosphorus reacts with oxygen to form phosphorus oxide, that is white solid, that is P4O10. Then the white solid, that is phosphorus oxide, reacts with water to form phosphoric acid. So phosphorus oxide reacts with water to form phosphoric acid, and then we have to balance it. Define weak Bronsted-Lowry acid. So as it is acid, therefore it is proton donor, and as it is weak, therefore it partially dissociated or partially ionizes in aqueous solution. Then define the enthalpy change of formation. So the enthalpy change of formation is the energy change or the enthalpy change when 1 mole of a compound is formed from its constituent elements in standard state. 1 mole of a compound is formed from its constituent elements in standard state. Then we have to use data in table 3.1, that is in this table, to calculate the enthalpy change of reaction. There is given R, that means it defines reaction. So we have to find the enthalpy change of reaction for this reaction. So we have first write this equation as given. Then here we have given in the table enthalpy change of formation. That means these compounds are formed. So for the formation of H3PO3, as it is formed, so the arrow would be towards this side or towards H3PO3. And here is a box, that is the reactants that causes this formation. But since we need to just find the enthalpy change of reaction and not draw the diagram, so we can ignore writing this. So as H3PO3 is formed from its reactants, and as there are 4 moles, so we multiply its value by 4, then H3PO4 is formed, so arrow is towards H3PO4. pH3 is formed, so arrow is towards pH3. And as it is enthalpy change of reaction, so it is from the reactants to the product side, so it is this side. Then we have to add this value that are in the same direction and then equate the value that are in the opposite direction. So these two arrows are in the same direction, so we add these two values then equal to the arrows that are in opposite direction and find our answer, that is enthalpy change of reaction, that is plus 54. Since the final answer is positive, so we write this as a given answer. You must have to write the sign because this determines whether the reaction is exothermic or endothermic. But since it is a 2-mark question, so you don't need to write these things, but to calculate this easily, you must write this for your understanding. Explain why the reaction 1 is a disproportionation reaction. So disproportionation reaction, as we can see that there is in reaction 1, so this is referred as reaction 1. So in reaction 1 we can see that the oxidation state of hydrogen remains the same, that is positive 1. So for phosphorus we can see that its oxidation state initially it was plus 3 and then it increases to minus 3, that is in pH3, and plus 5 in H3PO4 plus 5. So as we can see that phosphorus in H3PO3 is both oxidized, that its oxidation state increases, and its oxidation state decreases, that means it is reduced. So phosphorus in H3PO3 is both oxidized and reduced as its oxidation state changes from positive 3 to positive 5 in H3PO4 and negative 3 in pH3. Then figure 3.1 shows the reaction scheme that involves H3PO4 in several reactions. So here we can see that identify A which reacts with propene in the presence of H3PO4. So here we have given propene, that is we have drawn propene. Propane forms propanol. This structure is propanol because this is METH pro. So this is propane, and as this is hydroxyl group, so it will be propanol. So propane reacts with steam. So this would be steam at 450 degrees centigrade, 250 atmosphere pressure, and in presence of phosphoric acid to form propanol. Draw the structure of B. So propanol reacts with KBr in presence of H3PO4 to form, just as this reaction would be a nucleophilic substitution reaction, so the nucleophile Br minus would replace OH minus and would form Br, that is CH3 CH2, instead of OH it would be Br then CH3. So the structure would be CH3 C CH3 CH2 CH3 Br. So this structure would be the product, that is B. Since this is just a nucleophilic substitution reaction, name the type of reaction that occurs in reaction 3. So for reaction 3, this is reaction 3. Here acid reacts with alcohol, as this is alcohol, so acid reacts with alcohol to form ester, as this is COO group. So acid reacts with alcohol to form ester, thus this is esterification reaction. Also it is a condensation reaction since water is also formed. For esterification reaction, ester as well as water is formed, therefore this is condensation reaction. Condensation reaction is a reaction in which water is formed, and hydrolysis reaction is a reaction in which water is used. The reaction 3 is monitored using infrared spectroscopy. It is not possible to use OH group for the absorption frequency to monitor this reaction. If there would be OH group to monitor this reaction, then it would be easy because in product side there is no OH group, but in reactants there is OH group. So it would be easy to determine that the product is formed. But since we cannot use the OH group to determine the product is formed, so what can we use to detect that the reaction 3 is completed? So as we can see that for this, that is alcohol reacts with carboxylic acid to form ester, in all these three substances, that is in reactants and in products, everything is common except the carbon oxygen double bond and carbon oxygen double bond. That is, for ester, the carbon oxygen double bond is 1710 to 1750, and for carboxylic acid the carbon oxygen double bond is 1670 to 1740. Thus these two differences we can use to calculate or to determine that the reaction is complete. So we can use the bond, that is carbon oxygen double bond. So we can use this to determine that the reaction is complete or the reaction occurs, because the absorption changes to wavelength from 1670 to 1740, that is from carboxylic acid, to 1710 to 1750, that is ester, that is 1710 to 1750. So the reaction occurs and carboxylic acid, that is 1670 to 1740, changes to ester, that is 1710 to 1750. H3PO4 reacts with alcohol to form organophosphates, or organophosphates are similar to esters. So H3PO4 reacts with alcohol to form this ester. So this is given the structure of this ester. So here we have to complete the reaction. H3PO4 reacts with methanol. So here we have given the information for this reactants. We just have to write the products. So as for this structure, this group remains the same, except we just have to add CH3 group. So one CH3 at this side, one at this side, and one at this side. Then as there are 3 CH3, so we write the balanced equation, that is the product would be like this, and balance the equation. Then compound T is simple organophosphates or ester. Compound T is ester. Since organophosphates is similar to ester, so compound T is a simple ester. The mass spectrum of T shows a molecular ion peak, that is mass per unit charge peak, at the given value, that is the MR. This peak has a relative intensity of 12.7, and the relative intensity of M plus 1 peak is 0.84. Reduce the number of carbon atoms in T. To reduce the number of carbon atoms, that is to find the value of N, we know the formula, that is N is equal to 100 by 1.1, that is N is equal to 100 by 1.1 into M plus 1 peak by M plus peak. This value is for N, where N is the number of carbon atoms. So 100 by 1.1 into M plus 1 peak by M plus peak, that is 12.7. So we find our answer as 6.012, or approximately 6. So there are 6 carbon atoms. Thus we have found the number of carbon atoms, that is 6. Hence suggests the structure of the molecular formula. So for T, we know that the MR is 182. So the total value is 182, and we have 6 carbon atoms. So we minus this from the given value, as we know that there is already 6 carbon atoms. So we subtract this to find the number of hydrogens. So we subtract this, then we also subtract oxygen, as there are 4 oxygen. As this structure, for this structure, this group remains constant, so we subtract this group to find the number of hydrogen, that is subtract 4 oxygen, and the MR of oxygen is 16, and then subtract the MR of phosphorus, that is 31. Then after subtraction we get the value of H, that is 15. So it would be C6H, that is 15, and the given formula, or P and 4O, that is 4OP. So C6H15 4OP. So this would be the structure of T. Then in question number 4, lactic acid and pyruvic acid both contains 2 functional groups. So both of these 2 acid contains, for lactic acid there is carboxylic acid functional group and hydroxyl functional group. For pyruvic acid there is CO, that is ketone functional group, and carboxylic functional group. So explain why lactic acid exists as optical isomer. So optical isomers only exist when there is chiral carbon. That means a carbon atom that is attached to 4 different groups. So for lactic acid, here we can see that the chiral carbon is the center carbon, and this carbon is attached to 4 different groups, and no groups are similar. So this can form optical isomers. Because there is chiral carbon, or if we have to explain this, we can say that there is no non-superimposable mirror image. That means there is non-superimposable mirror image. We have to write this for the definition if it is 2-mark question. Then give the systemic name of lactic acid. So for lactic acid, as we can see that there are 3 carbons, so METH, ETH, prop. So propanoic acid, and as there is hydroxyl group, so we start counting from the more complex group, that is COOH. This is the more complex group. So from 1 2, so 2 hydroxyl propanoic acid, 2 hydroxyl propanoic acid. Then lactic acid can form hydrogen bonds with water. So here we have given the lactic acid, it forms hydrogen bonds with water, that is H2O, where we have to give oxygen delta negative sign, hydrogen delta positive side, again oxygen negative, hydrogen delta positive, then draw broken lines between hydrogen and oxygen and hydrogen of lactic acid and water to represent this hydrogen bond. Hydrogen bond usually occurs between hydrogen with oxygen, nitrogen, and fluorine. Complete the diagram in figure 4.5 to show the mechanism for the reaction of propene with bromine. So here this is propene, METH, ETH, prop. So this is prop, and as there is double bond, so it is propene. Propene and bromine, since it reacts with bromine, so the double bond, the curly arrow from the double bond would be at the delta positive ion, that is at one of the Br positive ion, and the other would be Br negative. So the double bond, curly arrow from the double bond is from the curly arrow and to the delta positive bromine, and the electron from this 2 bromine would go to the delta negative bromine. And after this step, the delta positive bromine is already bonded to this ion, that is the positive ion, and as this electron goes into delta negative bromine, so it would contain lone pair of electrons, and it is negative charge. So negative charge attached to positive ion by curly arrow, and this is our final product. So then we have to write an equation for the oxidation of lactic acid to pyric acid in 3rd step. So here we can see that in 3rd step, lactic acid is converted to pyruvic acid. In the 3rd step, that is lactic acid's OH group is converted to COO group. That is here OH group is converted to CO group, that is ketone. This occurs due to the reaction with oxidizing agent. So here we denote oxidizing agent as oxygen with a bracket. So CHOH, COH would be converted to COOH, that is OH group, and H is removed, thus OH and H group is removed, so water is removed and oxygen is added. So this reaction would be the reaction. Part B, question number 3, that is the last paper or the last part of this paper. Complete table 4.1 to give details of the reagent and the conditions used in the two synthesis of figure 4.3 and 4.4. So here we are given a set of reactions in figure 4.3, and in figure 4.4 we have to give details of the reagent and the conditions, that what reagents and conditions are used for these reactions. So synthesis of propene. So first of all we would deal with figure 4.3, that means this figure. So for this figure we can see that for the first step, reagent and conditions. So that means in the first step we can see that propane reacts with which substance to form this product, that is containing 2Br. That means it obviously reacts with bromine, and addition reaction occurs and double bond would break, and Br is attached to this carbon and this carbon. Thus it would react with Br, and no conditions is required, so just reaction with Br, that is already given. Then the second step, for the second step, that is this product reacts with which substance to form the product. Since we have not given the product, So we cannot deduce that which reactant or reagent can be used. So we left this step for now. Then we see on third step, oxidation occurs. As oxidation reaction occurs, so obviously oxidation occurs in presence of acidified Ka2Cr2O7. Whenever it is an oxidation reaction, it will always occurs in presence of K2Cr2O7 or acidified K2Cr2O7. Thus, after oxidation, this product is formed, that is CH3COCOOH. And after oxidation, this product is formed. And what is oxidized to form this product? So, obviously, this would be an alcohol because alcohol is oxidized to form this product. So, as it contains 3 carbon, so it would be a 3 carbon alcohol. Thus, it would be a propanol, and propanol containing 2 hydroxyl group since 2 CO bond are formed. So first hydroxyl group is in the second carbon and the second hydroxyl group in the first carbon. So this would be an alcohol. So alcohol reacts with oxidizing agent in presence of acidified K2Cr2O7 to form this product, that is pyruvic acid. Then for the second step, we can see that this Br compound reacts with which substance to form this alcohol, that is in the third step. So this compound reacts, as we can see that Br is substituted and OH group is added. Since Br is substituted and OH group is added, that means it is a nucleophilic substitution reaction. So for nucleophilic substitution reaction, we can use sodium hydroxide in aqueous. So we can use sodium hydroxide in aqueous for this nucleophilic substitution reaction. Then for the synthesis of ethanol, not ethanol, as there is COOH group, thus this would be an ethanol or an aldehyde. So this is the structure of ethanol, CH3COH. So this would be the ethanol that is given here. Then in the first step, ethanol is converted to a compound. Since we have not given this compound, so we left this step for now. Then in the second step, lactic acid is formed, and lactic acid contains COOH group and OH group. As we can see that lactic acid contains 3 carbon, while initially ethanol contains 2 carbon. That means one extra carbon is added, and this cannot be an esterification reaction because there is no COO group. So as there is no CO group, but since carbon is added, so this must be an CN group. So CN addition occurs. So addition of CN occurs, that means in the second step we can see that CN is added, and thus the first step would be HCN in presence of KCN catalyst. Here KCN acts as a catalyst and the reaction occurs with HCN. So KCN is catalyst for this reaction and reaction occurs with HCN. So this would be HCN in presence of KCN catalyst. Then in the second step, we can see that this product, that is the CN product, reacts with which substance to form this product, that is containing one OH group that is already given, and CN is converted to COOH group. CN is converted to COOH group. So as CN is converted to COOH group, that means it must be an acidic hydrolysis. That means CN reacts with water in presence of HCl or H2SO4 catalyst to form carboxylic acid. CN reacts with water to form carboxylic acid in presence of HCl or H2SO4. Thus it is an acidic hydrolysis reaction. This is acidic and this is hydrolysis, that means reaction with water. So this is acidic, that means in acidic condition hydrolysis or reaction occurs. So this, for acidic hydrolysis, CN reacts with water to form carboxylic acid, to thus aqueous HCl or H2SO4 is needed, or dilute H2SO4 is needed, and since it is aqueous or dilute, that means it obviously produces water or provides water. Then in the third step, this lactic acid is converted to pyruvic acid or this product. So we can see that lactic acid OH group is converted to COO group, and this OH group remains the same. That means the oxidation of hydroxyl group to CO group occurs. That means reaction with oxidizing agent, and whenever it is reaction with an oxidizing agent, So the condition would be acidified K2Cr2O7 acidified K2Cr2O7 for this reaction. This is not a catalyst, but this is needed for this reaction, that is acidified K2Cr2O7. Acidified K2Cr2O7 is needed for oxidation of alcohol. Acidified K2Cr2O7 is needed for the oxidation of alcohol to form carboxylic acid or COO group. That is this CO group. So alcohol is oxidized to form CO group by the reaction with an oxidizing agent in presence of K2Cr2O7.